Welcome to September 19th LeetCode Challenge, Distinct Subsequences. Given two strings s and t, return the number of distinct subsequences of s and t which equals s, which equals t. The string subsequence in a new string formed from the original string by deleting some, can be none, of the characters without disturbing the remaining characters' relative position. For example, the string ace is the subsequence of ABCDE, while AEC is not a subsequence. It is guaranteed that the answer fits a 32-bit signed integer. Alright, so we know we have given the string here there, and we've given the string rabbit, and we want to find the number of distinct subsequences we can make from a sequence of s, which equals to t. So how do we know how to do that? So basically we know that s is a subsequence of t is a subsequence of s. However, we have the b's here, which we can make basically three permutations of it. So we can use the first 3b, we can use the last two b's to make the rabbit here, and we can use the first b and the last b, right, not the middle one. So that's pretty much an overall example of that one. We have another subsequence here where we can make t from s. However, we can make it 5 times because we could use different permutations of the ordering of the string s, as long as we don't disturb the remaining characters in the lower relative positions, and we could delete some or none of it. Alright, and basically her constraints would be s and length of s and t between 1 and 1000, and s and t consists of English letters. Great. So you can see how we need to kind of iterate through the string s, and then we want to find if characters t we can make with it, right? How do we know if we can make something with it according to the permutations? Well, it would be best to kind of structure things into a dynamic programming array, and then what we're going to do is using a base case, right, where we're going to basically use a string, and we found the string at the end of t, then great, we add it to the increment the number of the output, and we're just going to keep count of it. So here's how I'm going to do that. So let's make a dynamic programming array where we say, let's call it the length s length t length. It's gonna be length s t. It's gonna be equal to the length of s and the length of t. So we want to make a dynamic programming array, so it's going to be an array of an array. So let's characterize that by having an array of zeros, initialize that, times the length of t plus 1, right? We want 1 over because the next 0 doesn't count, for each element or blank in the range of s, length of s plus 1. Do I need the length of? Yeah, we'll keep it there for now. Alright, so we have a dynamic programming array made, so we use the list comprehension to make an array of an array using the length of t plus 1 and s plus 1. And next, we need to be able to iterate through each element first and develop our permanent dynamic programming array. So we're going to do a first pass here for each element x in the range of, let's say, the length of s plus 1. We are going to update our dynamic programming array at x with the length of t, and that's going to be assigned to 1. So we're going to assign everything to 1 first for each character in s. So that's basically a base case on saying regardless of where the string s would be, if you found something in t, then it's a good. Then that means that we are on the right path, right? We have the right approach to it. By the way, I'm doing it an iterative dynamic programming approach, so I'm just gonna probably do a for loop here for, let's say, the element I for s in. So we would have to actually go. So since we need to be able to iterate in reverse direction to go basically to dynamic programming at index 0, 0. So we have to go in reverse direction, and that'll be the range of length s. And then another for loop here for element I of t in reversed order, range of length t. So we iterate through basically each element index in the reverse range of length s. For each reverse length of length t, we are going to update our dynamic programming at basically our index s, index t, and we're going to update that with the current dynamic programming at +1 and t. However, if, let's say, the string at index I of s, what am I doing? I could make this ij, but whatever, it's good for now. Now I'm going to change it. ij. Makes this easier to read. J. Let's see, if that's equal to index t at j, that means that the same letter, alright, that means you can make a subsequence from t into s that matches s, a subsequence of s that matches into t. Therefore, dynamic programming array at I j will be incremented by 1 because it is part of our count. Then programming at I plus 1 and j plus 1. Okay, at the end of all this, we want to return a dynamic programming array at index 0, 0, because that's what we're aiming for, right? We're going in reverse direction until we find the final answer, which is located in the beginning of the dynamic programming array. Let's run this. D is not defined. Of course it is not, because it should be dp. Yeah. Looks good. Accepted, awesome. So time complexity wise is going to be big O of m times n, where it would be basically the length of s times the length of t. Yep. Dynamic programming wise, space complexity will be big O of m times n as well. We have a double dynamic programming, two double dynamic, a dynamic programming array of a dynamic programming array. So we have two arrays here and nested within each other as well. So big O. So both for time and space complexity, be big O of m times n, where m is the length of the size of s, and m is the length of size t. All right, that's it. Have a great day, guys.